Okay, so we will continue. So I think we stopped on the pH electrode during that time. So we already has this so-called the membrane indicator electrode, or the so-called the ion selective electrode, as we have started last time. So there are two types of a pH electrode that you can have. You have one that is a two electrode system, one that contains the saturated calomel electrode and with the glass electrode, and one that just contains everything. Okay, the silver electrode, and we could say these pH glass membrane that we have here. So the question now is, how does this ISE works? Although we could say pH meter is the classic example of this ISE, or ion selective electrodes, there are other ISE that is, we could say, available. It just happened that the most common one is this pH meter. So if we're going to look at this ISE, okay, we can begin how it membrane electrodes are constructed and how they function by examining some detail the glass electrodes for pH measurements. Okay, so it started as early as 1930s when they found out that the glass electrode is much better in determining the pH. Okay, the most convenient way of determining the pH since 1930s, measuring the potential difference across a glass membrane separating the analyte solution from the reference solution of fixed acidity. So it was first recognized way back in 1906, okay, by Kramer, and then Haber, okay, the Fritz-Haber process of this ammonia fame, he systematically explored this idea later on, okay, until they developed this ISE. So the ISE, it responds, we could say, only to one ion. And if you're going to look at this ISE, it contains a thin membrane capable of only binding the desired ion. So there's no redox process here. Okay, so we could say this is preferential binding of the ion in the material that is given. So if you're going to look at this ion selective electrode, there's an internal reference electrode, some filling solution, and then an external reference electrode, and you dip both of them in the analyte. So if you're going to look at the ion selective electrode, so this is what you see. Okay, some filling solution inside the electrode, and then there's an inner surface membrane, then the ion selective membrane, the outer surface of the membrane. So you can put here this ion here as K plus, or this C6H5-4B minus, or valinomycin, and then you have here the outer one. So what is really happening here? Okay, so the membrane that you have there contains some sort of a ligand. So the ligand that you have in the example I'm giving is a valinomycin. So that specifically and tightly binds with the analyte of interest. So let's say the analyte of interest that we have here is K plus. Okay, so what happened? There are counter ions that you have there, which in this case is C6H5-4B minus. They can't cross the membrane. So maybe it has something to do with what? Why do you think they cannot cross the membrane? It has something to do with their size. Okay, and in addition to size, they have what? Low solubility in the membrane or analyte solution. So most likely they are insoluble. Okay, so what happened? There would be a difference in the concentration, okay, of your target analyte exists across the outer membrane, and the C plus, your target analyte, they would diffuses across the membrane due to the concentration gradient. resulting in charge difference across the membrane. So what mass transport do you have here? Anyone? Ano yung mass transport na na-generate ninyo dito?
Diffusion po.
Okay, so there's what we call the diffusion that you have there. A difference in the concentration. Okay, and then there's a potential across outer membrane depends on the C+ concentration in the analyte solution. So there's also a difference in the concentration here, okay, existing across the inner membrane. So as you could see here, the C+ that diffuses across the membrane due to the concentration gradient result in the charge difference across the membrane. So there is the generation of potential difference. So the potential across inner membrane depends on the concentration in the filling solution, which is a known constant. Okay, so any difference that you have there is determined by the potential difference between the inner and the outer membrane. So it's just between the difference that you have here in the what we call outer membrane and in the inner membrane, where the potential of the inner membrane is constant, and the potential of the outer membrane depends on the concentration of your target analyte, okay, in the solution. So that's how they generate the potential. Okay, so there's always a comparison doon sa inner membrane that contains the constant concentration of the analyte compared doon sa nasa outside membrane. Okay, that's how they generate this what we call the pH. Okay, and if you're going to look at it in terms of, we could say, a silver chloride, a reference electrode. So this is how the cell notation would look like. So as you could see here, the one that is participating here is not the silver, but the chloride ion. Okay, so that's the one that you have in the outer reference electrode. And then you have here the H+, that is the one outside the solution. And look what happened. There is also a glass membrane in between them. And inside that, you also have an H+. Okay. And in addition to that, you also have in the inner reference electrode, the chloride. Okay. So you could see here, the reference electrode that you have is what? The chloride. The one that you have on this part and this part. But the one that you're really measuring is the difference between this and this one. Okay. So if you're going to look at how the pH is determined, so usually we could say there's a formation of the boundary potential across the glass membrane. So whenever there is a charge imbalance across any material, there is an electrical potential across the material. So if you're going to look at this, this is what? This is the inner one, and this is the outer part. So in the inner one, you have a fixed or constant H+ or activity of your hydrogen ion. And outside, well, it depends on the analyte solution that you're measuring. So usually it is what we call different. Okay, so the concentration of your H+, or what is the other name for H+? A proton. Okay, inside the membrane, it's usually what? Constant. And the concentration outside is determined by the concentration or activity of the protons in the analyte solution. So the concentration difference produces the potential, okay, difference that we measure with a pH meter. And we could say at each membrane solvent interface, there's a small local potential developed due to the preferential adsorption okay, of H plus in the glass surface. So, ito yung nangyayari doon sa pH meter. Okay? So, this is fixed, constant, and then this is variable. So, any concentration difference, they produce a potential difference that we measure with a pH meter. So, ganun yung pag-ano no, pH meter. Okay? Now, we also have to take into consideration yung structure ng glass membrane. Because, as I mentioned, there are some H plus, okay, that we could say absorb in the glass surface. Why? Why do you think there is a selective binding of the H plus to the glass membrane? So if you're going to look at this, glass is made up of what? Anyone?
Silicate po.
SiO. Okay? It's not really the boron, it's mostly the Si. So if you're going to look at this, so it has something to do with the glass composition. So the glass composition, we could say, affects the sensitivity of membranes of protons, okay, and other cations. Now, Corning, which is glass manufacturing industry. Okay, so if you have, for instance, they have this Corning 0.1015 glass. Okay, they are the one that widely used for the membrane. Okay, the one that they use in pH meter. And usually it's made up of what? 22% sodium oxide, 6% calcium oxide, and 72% silicon oxide. So this membrane is specific in its response towards the H plus up to pH 9. What do you think happened at high pH? Saan na siya responsive? At high pH.
Sodium po, sir.
Okay? The preparation, the preference now would be towards the sodium. Okay? As well as to other singly charged cations. So yan yung composition Corning 015, the one that they usually use in most of these pH electrode. So it prepared to bind with the proton up to pH 9, but above that, it prepares to bind the Na plus, okay, and other singly cation. Now there are other glass formulation that is used in which sodium and calciums are replaced to various degrees by barium and lithium. Okay, and this membrane we could say have higher or superior selectivity at high pH. So if you're going to look at this, we could say image that you have there. So this is just the cross-sectional view of the glass silicate or the silicate glass membrane structure. So each silicon atom, as you could see there, okay, they are bonded to what? How many oxygen? 1, 2, 3. 1, 2, 3. 1, 2, kulang ng isa, and then you have 1, 2, 3. Okay? And in addition to that, each bonded to another oxygen above or below the flame. Okay, so I'm not sure if you can see this thing here in terms of the binding. So we could say, ano sa tingin niyo to? Is that the oxygen? And the blue one is the what we call the Si, and most likely, okay, the white one there, that's your cation. Okay, so the glass consists of this infinite 3D network of SiO groups in which silicon is bonded to 4 oxygens, and each oxygen is shared by 2 silicon. So within this interstices of this structure are sufficient cations to balance the negative charge of the silicate ion. So we could say this is more of what? Electrostatic. Okay, you have the Si and O that are negative, and then you have a positive cation. Okay, so there's opposite charges that attracts with one another. So that's why singly charged cation like sodium and lithium, they are, we could say, mobile in the lattice. And they are, we could say, responsible for the electrical conduction with the membrane. But why do you think H plus is preferable? And then Na plus and then Li. What do you think is the main reason? Anyone? As simple as Gen Chem 1 principle.
Comparable po sir yung size po niya.
Okay, it has something to do with the size. H plus is smaller than Na plus, which is smaller than, I think lithium plus is smaller than Na plus. Okay, it just happened at high pH, usually, I think the source of your base is usually an NaOH, so that's why Na plus is the one that is preferable there. Okay. And if you're going to look at the example that you have there, so it could be an H plus here or other cation. That could be sodium ion. Okay. So it's usually surrounded in what? In a cage. So parang they fell into a cage here. Yung malaki yung butas. Okay. So I would say the composition and the structure of the glass membrane has something to do why they prefer to bind with H plus and Na plus. And then we can look also at the so-called hygroscopicity. So you know the word hygroscopic? Which compound is usually hygroscopic? That's why we need to standardize if we prepare a solution of that compound. Anyone?
Sodium hydroxide.
Okay, it's sodium hydroxide. You cannot leave sodium hydroxide standing in open environment, because what will happen is after some time it's going to absorb moisture. Okay, so if you're going to look at the hygroscopy of hygroscopic nature of the glass membrane, so usually the surface of the glass membrane, they must be hydrated before it will function as a pH electrode. That's why you cannot let it dry. Okay, because non-hygroscopic glasses would show no pH function. So even hygroscopic glasses, they lost their pH sensitivity after dehydration by storage over a desiccant. So what is the main rule when you have a pH meter or a pH electrode? Most of the time, it should be stored in a solution. Okay? Because if you let it dehydrate, it will affect the sensitivity. Why? Why do you think? What happened if it dehydrate? Ano ba meron sa pH meter? Di ba may H plus siya doon, solution sa loob? So if that pH meter dehydrated, you will lose that. So what will happen? Hindi na tama yung reading. Remember, the reading is based on the concentration of H plus in the analyte and compare it with the concentration of the H plus doon sa inner membrane. And if you are not able to keep it hydrated, so there will be what we call a problem. Okay? The effect, they said, is reversible, however, and the response of a glass electrode can be restored by soaking it in water. So even if you what we call let it dehydrate, once you put it in water, it will what we call do the reading again. But okay, you have to what? What do you usually do to make sure you get the correct reading? Anyone?
Calibrate po.
Okay, you calibrate it with pH 4, 7, and 10. Now, if you're going to look at the hydration of the pH-sensitive glass membrane involves an ion exchange reaction between singly charged cation ions in the interstices of the glass lattice and the protons from the solution. Okay, so we could say there's no redox reaction here. It's mostly on the attractive forces that you have there, the electrostatic, the ion exchange. So you have the H plus in the solution. You have an Na plus there in the glass membrane. So there's an exchange that you have there. So the H plus will displace the Na plus. So the equilibrium constant for this is what? They said it's so large. So what does it mean if you have a large K? Okay, it's the name of a bond, one direction reaction. Kapag matlaki yung equilibrium constant mo. So that means that the surface of the hydrated glass membrane ordinarily consists entirely of silicic acid. Yan yung tawag dyan. Yung silicate tsaka H plus. So you call it the silicic acid. Now, if you're going to look at what we call the electrical conduction across the glass membrane. So for the glass membrane to serve as an indicator for cations, it must conduct electricity. And the conduction within the hydrated gel layer involves the movement, okay, of the hydrogen ions. So usually the sodium ions are the charge carriers in the dry interior of the membrane. And the conduction across the solution gel interfaces occurs by this given reaction. The H plus reacting with the silicates to produce the silicic acid. Okay, so that's how the electrical conduction would happen. So H plus, we could say the glass H plus, and then we could put them. I think it should have been H plus, Gl minus, and then it can also be so. What do we see here? So this one might be happening between the glass membrane and the analyte. And the second one is happening between the glass and the internal solution. Remember this one? So the first one happened here. The second one is happening on this one. So we could say that's the first, and then that's the second, the interaction that you have here. Now, since they are what? Reversible. Okay. Which do you think decide the position of these two equilibrium system? What do you think happened, okay, to the positions of these two equilibria? They are determined by what? They are both determined by the H plus on the inner and the H plus on the outer membrane. Okay, the surface at which the greater dissociation occurs becomes negative with respect to the outer surface where less dissociation has taken place. So the dissociation which usually takes place in the glass membrane and in the inner solution, because what's happening here is the binding of H plus with the glass membrane. So you can still develop something here in between. Kasi parang may junction sila dito eh. Okay, so we could say that's a boundary potential that you have there that is happening, okay, across the membrane, and the magnitude of this boundary potential depends on the ratio of the hydrogen ion activities of these two solutions, the outer and the inner. So if this potential difference that serves as the analytical parameter in potentiometric measurements of the pH with the membrane electrode. Okay? So yung potential na nag-rise up dito between the difference of the H plus here and the H plus here, that's the one that will tell you, okay, what's the pH measurement is. And they said there are usually what? Several potentials that you can develop, okay, in the membrane. So you can have the potential of the two reference electrode. So it depends on the electrochemical characteristic of the respective redox couple. So you can have the reference electrode one here, okay, and another that you have here. And then you have the potential across the glass membrane. So this depends on the physicochemical characteristic of glass and its response to the ionic concentration on both sides. So the one that happens in the redox is in the reference. The one that happens in your glass membrane, that's the one that is based on the physicochemical characteristics. So where do you find that thing here? So this is the one that you have. No, not that one. I think it's something to do with this one. So you have one potential, two potential, three potential, and the fourth one is the junction potential. So this is across the, sana de-developing junction potential. Salt bridge. So the salt bridge that separates the two reference electrodes. Okay, so the last one that you have there, the EB, that is your boundary potential. So this varies with the pH of the analyte solution. Okay, so ano role ng reference electrode? What do they do? Anyone? So they do what they're called reference. They provide some sort of an electrical contact with the solution so that changes in the boundary phase or the boundary potential can be measured. Okay? So yung role nung tinatawag nating reference electrode. And if you're going to look at these four potentials, so two of them are the reference electrode potential. They are usually what? Constant. Okay. The third one, that is the junction potential that's across the salt bridge that separates the calomel electrode from the analyte electrode. And the fourth and the most important potential is the boundary potential, which varies depending on the analyte solution pH. And they said pH is determined by the formation of potential across the glass membrane. And if you're going to look at the boundary potential that you have there, so this is just the same that you have here. Reference electrode 1, reference electrode 2. And what do we have here? We have the subscript 1 and subscript 2. So this is the one that appears in the two surfaces of the glass. So this is in outer, and this is the one that's happening in the inner. So your proton or H plus in the solution binding with the glass membrane, and then your glass membrane dissociating, okay, and the H plus in your what we call inner membrane. So these two reactions cause the two glasses, two glass surfaces to be negatively charged with respect to the solution with which they are in contact. And if we're going to continue, the resulting difference in this potential between the two surfaces of the glass, which is the boundary potential. So this is related to the activities of the hydrogen ion in each of the solution by Nernst-like equation. So we can put it as what? EB equals to E1 minus E2. Okay. If you're going to look at this, this is just equals to 0.0592 log of activity 1 over activity 2. So if you're going to look, where is this activity 1, activity 2? So if you're going to look at the cell notation, so this is activity 1, this is activity 2. Okay, so A1 is the activity of the analyte solution, and A2 is that of the internal solution. And for a glass electrode, pH electrode, the hydrogen ion activity of the internal solution is held constant. So if you have that in terms of what we call constant, so you will say EB equals to L plus 0.0592 log of A1. Okay. Or we could say L is equals to 0.0592 pH, or L is just equals to 0.0592 log of A. And the boundary potential then is then measured of the hydrogen activity of the external solution, which is your A1. So that's the, we could say, boundary potential. Now, what's the significance of the potentials and the difference here? This could lead to what we call the asymmetry potential, as shown here. So, as I've told you, the glass is the one in between. Okay. So you have the analyte solution here, and then there's this what we call internal reference solution. So when there's identical solutions are placed between the two sides of a glass membrane, the boundary potential should in principle be 0. Okay. However, we frequently encounter a small asymmetric potential that changes gradually with time due to the slight imperfections of the membrane. So if you have a perfect membrane, it should really be what we call 0. But since glasses, okay, not all of them are perfect glasses. So there's some imperfections, okay, which leads to a small asymmetry potential. So if we're going to look at this, so what do we see here in what we call the A portion that we have? Okay, so you have here E1, E2, that's the reference electrode, and this is the boundary potential that you have there. So this is an A1 equals to 10 A times A2. So what happened? Okay, so you have here the sources of this asymmetry potential, and it's still a little bit not clear, okay, how it came into being, but the difference in strain on the two surfaces of the membrane created during manufacture, mechanical abrasion of the outer space during use, and chemical etching of the outer, what we call surface. I think that's the possible reason why you don't have what we call the same or a perfect glass. So what do they usually do? They try to eliminate the bias here. Okay. So how do you eliminate the bias? If you see an imperfection between the two sides here, how are you going to eliminate them? Anyone? You need to do a calibration. So you have to calibrate it with one or more standard or analyte solution. Okay. And you have to do this calibration every day and more often, okay, when the electrons receive heavy use. So that's the way to at least overcome this imperfection. Okay. So if you always use it, you have always to standardize it because you're exposing it to the analyte that it has. So that's the way to overcome this asymmetric potential. Okay. So if kung perfect lang yan, I think there's a symmetrical potential that you have, but not all glasses are perfect on both sides. Now, as noted earlier, we also have this potential of a glass indicator electrode, which is E indicator. And they have what? Three components. You have the boundary potential, the potential of the internal silver reference electrode, and the small asymmetric potential, which changes slowly with time. So we could say, we can put this as the indicator potential equals to boundary potential EB, and then you have what? E reference to, since that's a silver fluoride, and the small asymmetry potential. So these are the three components of your what we call glass electrode. And if we're going to substitute this, so you have the L. This one is 0.0592 log of A. And then E reference 2 plus E asymmetric potential. Or we can put it as E equals to L plus 0.0592 log of A1. And we could say that this also equals to L minus 0.0592 pH, where L is just a combination of what? L prime, E rep 2, and asymmetry potential. So if you recall the metallic cation indicator, okay, they are similar to what we have here. But the main difference is the sources of the potential of the electrode that they describe, they are totally different. One is a redox potential in the metal, and here, this is what? The boundary potential. So the glass, I would say, is the one that plays a important role in the pH electrode. Have you seen the glass membrane of a pH electrode? Yung totoo. Have you experienced, I don't know, maybe you see most of them black one, but if you open it, it's just like a smoothen. And it's so thin. Wala? Hindi nyo nakita? It's so thin that most of the time students would break it. Sometimes they're not what we call careful in utilizing this pH meter. Most of the time they just break it, and sometimes they wonder why they break it. O at least mga student dyan umaamin dito kung pwedeng makalusot, makalusot. I remember when I was in UV, one summer, nakabasag ng burette yung estudyante, nakita namin ng student assistant. Tapos sinabi lang kami, I don't know why it's broken. Tingin na kami ng student assistant ko, what? Kitang-kita namin. What? Because burette, I think during that time is the expensive in the glassware around, during the time it's $20. I don't know, right now it's so expensive. As I've told you, the fluoride electrode, when the lab supervisor told me, how much is that? I think it's just 500. And when I look at BWR, oh my God, it's already 1.5. Sabi ko, sana hindi malaman yung kinuha ko. Okay, so that's how we could say sensitive the glass pH electrode. That's why they prepare right now like the pencil type. Even if you look at the aquarium type of this pH electrode, you could see that parang ganito, tapos meron siyang Holland. Tawag namin Holland. Okay, but that is what we call fragile. Okay, so what are the possible errors in this what we call pH measurements? Ano yung mga possible errors na meron sila? So I list down some of them here. Okay, so I think one of them has something to do with the standards. Okay, so what's the problem with the standards? So if you're going to look at this, what we call error that they have, some of them are standards, junction potential, the junction potential drip, equilibration time, hydration of glass, temperature, cleaning, alkaline or sodium error, and what we call the acid error. Okay, and then you may ask yourself, so how are these what we call conditions affecting the error that you have? Try to get my notes. So if you're going to look at the errors that you have there, in terms of these standards, the pH measurements cannot be more accurate than the standards. Okay, so there should be a difference of plus or minus 0.01 if you want to read it with respect to the standards. Okay, now in terms of the junction potential, as much as possible, the ionic strength, if ionic strength differ between the analyte and the standard buffer, junction potential will differ, resulting in an error of plus minus 1.01, not 1. So you might say so small, right? Kasi pH usually, how many decimal places your pH meter? Usually you have around 2 decimal places. I have not experienced 3. I think that's the common pH meters that you have, 2 readings. So if you have a standard error or junction potential error, so the difference is around 0.01. Okay. Now, how about the junction potential drift? What do you think caused that? So kapag junction potential drift, so it has something to do with what? Pag junction potential. Ano nagkakos sa tingin nyo? The drift of the junction potential. So usually it has something to do with the concentration of what? Anyone? The salt bridge. So ano usually mangyayari? The salt bridge can interact maybe with what? Ano yung common sa salt bridge tsaka sa reference electrode? That one. So if there is, we could say, changes in the KCl concentration and the silver chloride concentration, it can cause by slow changes in that concentration. So the way you're going to fix it is you will calibrate. Okay. And then equilibration time, what it is. Whenever you use an instrument, what do you usually do? Like UVBs. Wina-warm up nyo ba or pagka-on, gamit agad?
Warm up.
Okay, so you warm it up. So the same thing here. Okay, you want it to take a while for it to equilibrate itself. Remember, okay, the system depends on 2 equilibrium system or 2 equilibria processes. Okay, so you have to what we call wait for sometimes until they are ready. And even when you dip the pH meter, you will see it keeps changing, right? Until you see what? A constant. Okay. So in terms of this, what we call equilibration time, it takes around what? 30 seconds to a minute for electrode to equilibrate with the solution. Hydration. How does it affect? So kapag dehydrated or dry yung electrode mo, it will not respond to the H+ correctly. Okay? Temperature. How are you going to solve this one? How does it affect? So what's the effect of temperature with the potential? Is it dependent or independent of temperature? Does temperature affect the potential directly or it has no effect? So usually potential is affected by the temperature. Okay, so whatever happened, a calibration needs to be done at same temperature of measurement. Okay, cleaning. How does it affect the pH measurement? So if you clean it, sometimes you add contaminants to it, okay? It causes the reading to drip until it is properly clean or equilibrate with the analyte solution. And then the alkaline or the what we call sodium error. So if you're going to look at this happen when there is what? High or low H plus?
Low.
So if you say low, anong ibig sabihin yan sa pH?
Mataas po ang pH.
High pH, which is low H plus. Okay. So the way that you look at this, what we call sodium error, I'm going to discuss. I think I have a slide on that one. Okay, at low or very low H plus, the electron would respond to Na plus, and the apparent pH is what? Lower or higher than the true pH? Anong effect ng alkaline? Is it lower pH or higher pH than the true pH?
Lower po, sir.
Okay, so usually it is a lower pH than the true pH. And yung acid error, it will give you a higher pH when it should be low pH. So acid error, you have a high H plus, so the measurement of pH is higher than the glass pH. Usually, what happened at high H plus or low pH? Ano nangyayari dun sa glass? Based on Chem, pag masyadong madami kang ano doon, the glass become saturated with H plus. So those are some of the error, and I think I have a specific example here doon sa alkali error. So usually it exhibited at pH more than 9. And the electrode would respond to H plus and alkali cation. So if you're going to look at this, they run some of the common pH meters that they use, like the Corning 0.015, okay, at 1 dip at H2SO4, HCl, 1 molar Na plus, the Beckman GP, 1 molar Na plus, and then LNN black dot, Beckman type B. You look at the reading that they have. The C, D, E, and F, all of them, when you put them in the Na plus, what happened? The measured value is lower than the true value. Okay. So the electrode also responds to other cation. So what happened? Okay. In basic solutions, the glass electrodes responds to the concentration of not only H plus ion, but the alkali metal ion. At high pH, the glass electrodes indicate pH less than the true pH. So how can you explain this alkaline error? Ano nangyayari doon sa equilibrium? So we have the H plus, GL minus, and then we could put what? A B plus. And then we have this. So what is B plus here? Another cation, like sodium. So what happened? The electrode would respond both to the H plus and the B plus. So this usually happen, okay, when you have a high pH. Or when your H plus is significantly low, very low. So if you're going to look at this, look, C, D, E, F. So all of them has this what we call error. So dito naman yung error kasi lahat sila acid. So that is the alkali error. Now for the acid error, this is being exhibited at pH less than 0.5. So the typical glass electrode exhibit an error opposite in sign to the alkaline error in the solution of pH less than 0.5. So here you could see here the AB, because that's the one that you dissolve in the acid. This is just the same as the one that you had earlier. Iniba lang yung kulay. And it has something to do with the saturation effect. Okay. So the negative error that you have there, pH reading, is really higher than the true pH. So it indicates that the pH reading tends to be too high in this region. And the exact cause right now is still not known, but saturation effect is one of the culprits that they have. Now, how do you think you can eliminate this, what we call error? Let's say, how do you think you can eliminate alkaline error? Maybe you change what? The glass? Instead of what? The Si or silicate, you can use an Al2O3 or a B2O3. And if you have this, what we call the material, it enhances binding for ions other than the H plus. Okay, so it can eliminate the alkaline error in glass electrodes. Now, other glass electrode that permit the direct potentiometric measurement of these singly charged cations, they have been developed. So there are, we could say, particular glass composition or a particular glass composition of glass that is used for other cations like sodium, potassium, ammonium, and other stuff. So those are what we call the errors that you can find in the pH meter. Okay, and another thing that they included is this in terms of the effect of the alkali metal ion on the potential across a membrane. Okay, you have this so-called selectivity coefficient. So when we're talking about selectivity coefficient, it just says that no electrode responds exclusively to one kind of ion. Okay, although they said the glass pH electrode is among the most selective, it still responds to high concentrations of the Na plus. And when an electrode used to measure ion A also responds to ion X, then the selectivity coefficient gives the relative response of the electrode to the two different species. Okay. So the value that you have in terms of the selectivity coefficient is what? If this is your target one and this interfere, so your K value should be what? Higher or lower?
Low po.
Okay, so you want this to be higher and this one to be lower. So the overall thing that you have will be lower Ka. Because the lower or the smaller the selectivity coefficient, the less interference by X. And usually selectivity coefficient would range from what? 0 to values greater than unity. Okay, so if you're going to look at the selectivity coefficient of unity, means the electron responds equally to both your target analyte and the interfering ion. So unity, what is that? 1, right? So if you have a selectivity coefficient of 1, so that means pareho silang nagre-respond. So it's not good. Now, if an electrode responds, let's say for an ion X, 20 times strongly than ion A, then what do you have there? 20. So is that good? It is good to be used for X, but not A. That's the interpretation of it. If you want to answer it in an affirmative way, that it is good. Okay, that means it is selective more on X compared to A. The value here is 20. But if the value is 0.001, so what does it mean? That's what you want. Because that is equals to what? 1 here and ano yung value sa baba? 1,000? 1, 10, 100, right? Tama ba? So if you have a value of selectivity coefficient of 0.001, so that means 100 times preference sa A compared to X. And I think that's good. Now, how does this, we could say, selectivity coefficient included here? So we have this boundary potential, then you have the L plus 0.0592 log of A plus K H B P1. So KHB, that is the selectivity coefficient. So that's an additional term to measure the response of your ion selectivity electrode to other ions. Question? Yeah, that's the one that you have here. So KHB 0 means no interference. More than 1, there is interference. Less than 1 means negligible interference. Question before we go to another type of this membrane electrode. So these are based on the crystal. So if you have a crystalline membrane electrode, so usually Okay, they are solid state electrode. So most important part of the crystalline membrane is manufactured from an ionic compound or a homogeneous mixture of ionic compounds. Okay, in some instances, the membrane is cut from a single crystals. In others, these are formed from the finely ground or crushed powder, okay, of crystalline solid by high pressure or casting from what we call a melt. So you melt them and then you allow it to form again, okay? And sometimes you dope them to increase their conductivity. Now, the operation of this is similar to this, what we call glass membrane. So typical membranes, they have a diameters of around 10 millimeter and a thickness of around 1 or 2 millimeter. So parang ganun kaliit. Tapos yung thickness niya, 1 to 2 millimeter. Okay? And the characteristics of these solid state crystalline electrodes, if you're going to look at this, so you use this at these different analyte. So most of them are what? Ion, because we're still in the ion selective electrode. Now, if you're going to look at this, although there's a target analyte, you always have what? Interferences. Okay. And if you're going to look, there's some sort of a concentration range. And usually it's 10 to the 8 to 10 to the 0. So for the fluoride ion, usually they use these certain earth fluorides. The silver ion, they use silver halides and sulfides. And the copper ion, they use the copper sulfide. And I would say most of them, they have this plastic component, the Teflon or the PVC. Okay, so if you're going to look like a typical crystalline membrane electrode, so this is how it looks like. So you're going to look at it, there's a single crystal, the lanthanum fluoride. Okay, so this is how you look at it there. So it's an all solid fluoride electrode. Okay, there's no electrolyte here, so all of them are what we call solid. And you can have the silver fluoride and lanthanum fluoride that you have. So if we talk about this fluoride electrode, okay, so you have there your lanthanum fluoride that is doped with uranium fluoride. Now, uranium fluoride, we could say, has less charge than the lanthanum 3+. So an ion vacancy occurs for every EU2+. Okay, because there's a deficient in the charge, right? 2+ is what? Less than 3+. So a neighboring fluoride can jump into the vacancy, thereby moving the vacancy to another side. So repetition of this process is move the F- through the lattice. So you have there a silver chloride internal reference electrode, and then the reference solution, usually a fluoride, that's fixed. And then you have the crystals and you have the analyte solution. So think of it as this one replacing what? Doon sa pH meter. Your glass membrane. Okay. And if you have a commercial lanthanum fluoride electrodes, usually they're rugged. You can use it at 0 until 80 degrees Celsius, and the response is linear down to 10 to the -6 or 0.02 ppm. Okay. So the solubility of the lanthanum fluoride begins to contribute to the concentration of the fluoride ion in the analyte solution. Now, the only ion that can interfere directly with the fluoride is hydroxide ion. And it becomes serious at pH more than 8. Why? What happened at pH more than 8? There's more hydroxide. At pH less than 5, hydrogen ions can also interfere. Okay. And under these conditions, what you're going to do is you have the undissociated HF forms, and the electrode does not respond to the species. So at low pH, your fluoride will react with the H plus. So what will happen? There is no response because there is no F minus. Okay, the F minus reacted with the H plus. Okay, so that is, we could say, the crystalline one. And if we're going to look at the formula that you have here, so again, you could say there's an indicator that you have there, and then the L 0.0592, okay, times log of 1 over activity of the fluoride ion. Or if you're going to change the sign, you have what? 0.0592 log of A minus, or L plus 0.0592 the P of F. So that's the what we call the crystalline membrane electrode. And there's another set of this, what we call crystalline membrane electrode. I didn't include them. So usually they are what? The one that's based on silver salts. So since they are made up of what? Silver salts, so you can use them towards silver and halide ions, but their behavior is far from ideal. But they have some property, okay, that is, we could say, advantageous to them. Low conductivity, low mechanical strength, and a tendency to develop high photoelectric potentials. So what is good with the silver halide? What can you say about silver halide? They are what? Based on the solubility rule.
Insoluble po.
So they are insoluble. Okay. So sometimes you prepare one that is not going to dissolve in your sample. In spectroscopy, we always laugh because I think one student, why is my sodium chloride glass window being dissolved? Well, what do you think? What do you add to that window? I told you to use the silver chloride window. And he's using water or aqueous solution most of the time. So from time to time, it dissolves the sodium chloride crystal window. Because in the IR, we track our sample between the cell window. So usually we use silver chloride if it's aqueous. Okay. So I'll stop here. We're going to finish the next one because this is everything that we have. I also included here what the potentiometric. So hopefully I can get a photo when you do this potentiometric titration. Because I think, do you have a potentiometric titration using pH meter or wala?
Meron po,
Gumawa
sir.
kayo ng ganito?
Yes po.
Or tinaptalin again?
Meron naman po, sir.
Meron? Because you
Hindi
can
lang
present
po
it with
maganda
this
yung
one.
data.
Huh?
Hindi lang
Then
po
a
maganda
first
yung data.
derivative, a second derivative, and I think, I'm not sure if you're familiar with the grand plot. Okay, and how it's used in the redox titration. Okay, complexometric titration, and yung dapat last Saturday, but NYC was Water World last Friday. So we have to do the class online. So hopefully my students will be able to get a good data, but I always, because the question that you may ask here, so how do you know the endpoint if you're doing what? A precipitation titration, because when you add the silver nitrate with the halide sample, it's already precipitate. Okay. I always tell that to my students, and after they done the experiment, they still have no idea how they know the endpoint. Okay, so question. Lahat ba may ano na? Topic? Parang 8 lang ata yung nag-submit ng topic, if I'm not mistaken. And I uploaded already para makapagsimula na kayo. Nasaan na yun? The guide to the article review. Hindi nagbukas. So maybe you can start doing it. So the main reason why you want to do the article review is to see, okay, how the method that you're reviewing is better than the previous methods or other methods. So when you say other methods, you don't need to just compare it with another electroanalytical method. You can compare it with what? Spectroscopic method, LCMS method, or chromatographic method. Ang ano naman, ang idea naman ng we could say electroanalytical is you can do it in situ. And the always we could say disadvantage about it is its detection limit. You cannot go as low as the what we call one that you could see in LCMS or chromatography, especially if you have an LCMS detection. So in the introduction, you can write something about the compound or the group of compounds, because I think some of you are working on some group of compounds, and the method usually used to analyze them. Okay. And in the review of the article here, you write the advantages and the disadvantages of the method discussed in the paper. I think one of the main advantages of electroanalytical is the cost. It's usually low cost or cheap, but don't write the word cheap. Kasi magiging cheap ang paper natin yung review ninyo. Okay, so you can discuss other methods outside electroanalytical, usually the routinary method to analyze the compound utilized, but you have a paper where it use electroanalytical. You're going to expand this idea based on your review. Will having this new method makes the analysis faster? I think that's one of the main advantage of electroanalytical. However, is the detection limit needed higher than the other method? So these are the, we could say, questions that you need to answer in the review. So at least you start doing something habang wala pa kayo exam. Tanong? Bago mag-ano si Carmel?